So good evening. My name is Paul Lowe. I'm a senior lecturer here at the Melbourne School of Design. And before I introduce Immanuel, I would like to acknowledge the traditional owner of the land, the Wurundjeri people in which this meeting, where I'm currently at, is taking place, as well as the multiple lands given the location of all of us online. I pay respect to both past and present, and extend that respect to other Indigenous Australians present. So this evening, we're delighted to have Immanuel KOH with us for the last of the AA Visiting School lecture series. I know Immanuel through conferences, an annual Cadres conference organized by the Association for Computer-Aided Design in Asia. His work is of great interest to me, exploring AI in forms and images generations to extend our understanding of topological morphology. He uses technique of sampling to question canonical spatial syntax from Le Corbusier to Mies van der Rohe, and I imagine that he might delve a little bit deeper into this in this lecture tonight, titled AI Sampling on Plasticity and Form. Immanuel holds a joint assistant professorship between the School of Architecture and Sustainability Design and Design and Artificial Intelligence at the Singapore University of Technology and Design. Before this, he was based in EPFL in Lausanne in Switzerland, doing interdisciplinary research work between the School of Computer Science, the Institute of Architecture. His doctorate studies interrogated the epistemology and formal basis of architecture by reformulating a new design theory to the conceptual and algorithmic lens of architecture sampling in machine learning. He was a graduate from the Architecture Association's The Design Research Lab, and has since taught at the EA, the RCA, Tsinghua University, DIA, Bartlett, and Harvard GST, and many others. His work has been exhibited internationally as well at the V&A Museum in London and published widely, including Architecture Design and Design Computing and Recognitions. He's also the co-founder of the Neuroarchitecture Groups, the world's first repository and discussions platform for AI impact on architecture. Towards the end of these sessions, after Immanuel's lecture, we will have a discussions and Q&A sessions with Immanuel. So audience, if you have any questions for Immanuel, please use the Q&A functions at the bottom of the screen, and Mon and I will moderate the conversations. So without further ado, I'll pass this to Immanuel.
All right, thanks, Paul, for the very nice introduction. I think let me share my screen now. Just give me a second. Right. Yeah. So thanks the Melbourne School of Design for this invitation and the visiting school. I'm very happy to have this opportunity to share my thoughts and also recent work on the subject of AI and architecture. More specifically, the machine learning and deep learning as an emerging paradigm for architecture design and thinking and also practice. So for this lecture, I will in fact start off with by covering a few concepts, I think quite important concepts. In a way, I think it shows that these are the concepts that underpinned much of my approach in computationally design methodology. Sorry. So I think I will start by just dissecting the lecture's title and the subtitle. AI sampling on plasticity and form. So actually, the promo or background image that you saw when you signed up for this event is partly taken from the AI Sampling Singapore project that is currently on display at the 17th Venice Architecture Biennale, the Italian virtual pavilion. It's called the City X Venice, curated by Tom Kovac and Alessandro Malis. Actually, more specifically, it was curated by Matias Del Campo, who is also one of the members of the Neuroarchitecture group, alongside Sandra Menninger, as well as Daniel Bolojan. So similarly, it was also taken from, for those might have participated in the Digital Future World workshop. I think just a few weeks ago it ended. Mine was one of the several workshops, also called AI sampling. Now, the subtitle, however, is something that I've been thinking for some time, and I would like to share this with the audience. So the subtitle, however, is a reference to the well-known 1917 book by Darcy Thompson called On Growth and Form. I'm sure those who have worked on computational design would be quite familiar with this. The idea, Thompson basically used ideas from mathematics and physics in a way, appropriate them to discuss the global question of biological growth and form. In a way, if you look at his earlier papers, one of which titled Some Difficulties of Darwinism, he actually argued that the physical forces, in fact, may be the one governing biological form rather than evolution or adaptive evolution. So the idea is to kind of, the form itself is shaped less by these evolutionary functions, but more by mathematical laws. In other words, form follows growth, not function. And in fact, growth and transformation can also be understood as a continuous plasticity, especially in view of the more recent. You've probably seen some interesting companies or workshop doing this rewiring of your brain, which is essentially what neuroplasticity is about. The idea that you could rewire, even as an adult, you could rewire your brain. And this is very interesting because growth then is understood as also a reorganization rather than arriving at an optimal form, which is the case for evolutionary algorithm, for instance. And therefore, it could include the adding and subtracting of neurons, the connecting or disconnecting of synapses, the mapping or remapping of function, the brain function. So a kind of common definition goes like this. Neuroplasticity, also known as neuroplasticity or brain plasticity, is the ability of the neural networks in the brain to change through growth and reorganization. So the key thing is creating new pathways and also remapping of the original function of the different parts of the brain. And the idea is that in the past, we would think that, well, before epigenesis, we think that the brain is pretty much kind of decided after, say, the first 2 years of your life as after being born. But actually, it's not true. And this is really exciting because if we were to likewise conceive our computational design tool as a brain machine capable of changing continuously, well, for good or for worse, and in response to what you could experience in the case of deep learning would be the data sets that we're feeding it, then the process of generative design or the programming of form is no longer deterministic in form and function, but more importantly, it is in fact stochastic, or in other words, probabilistic, as well as cybernetic, because it interacts with the environment, it changes its state, and at the same time, it works with probabilities. Beyond neuroscience, the French philosopher Catherine Malabou actually extended this beyond the biological into the aesthetic, into the ethical, into the political. So the key reference here is what shall we do with our brain? So it's an active. So we no longer, if we're going to relate to our computational tools, we no longer just say what do we do with that tool. We would say how do we change it, right? How do we train it, right? To use a more specific jargon in deep learning. And in fact, the word plastic in French also comes from the other two words, which is plasticage or plastique. which essentially means something that is in fact destructive, which is not surprising because we know that Malibu was in fact an ex-student of Jack Derrida. And the very fact that she talked about this idea of this two extreme of taking form, as well as this explosion of the form, this instability of the form, just like what the brain could choose to move or rather be developed in a different way, it has that propensity as well. So I think in the first part of lecture, well, at least in one third of the lecture, or one quarter of it, in fact, I'll talk a bit more about the kind of underlying theoretical framework or the influences that, in fact, in the end would be quite critical to understand the computational methods. So for architects who are pretty familiar, right, with the Neoplasticism from Piet Mondrian, in his idea is that architecture is in a good position, unlike painting, because we're inherently dealing with something that is artificial, or we do not have the burden to represent the natural. And so the idea is that the new architecture for him, well, that was 1920s, is that the new architecture should destroy the work of art. Or we could put it in another way, is the decomposition or the kind of decomposition or the vectorization of form, at least in my context. So and lastly would be Theo van Donspoort manifesto towards plastic architecture, who saw architecture as something that is essentially elemental in the widest sense. So meaning we could go actually beyond the categories of beam, for instance, right? Something that's more basic. But what is basic about architecture? And the idea here is the need for, well, to use the word elemental, to elementarize architecture form would in fact be critical for the sampling of architecture form with machine learning and deep learning. Or for example, we could frame it in more specific AI jargon that would mean encoding or embedding of forms as numerical vectors. So what is sampling, right? Let me keep track of the time. I often show this slide because it is kind of a different emphasis, and the musician did it earlier, right? Even the idea of using a sequencer, a sampler, a synthesizer, it was in the late 70s. So we're kind of moving beyond that, just drawing. In fact, we're also trying to move beyond the symbolic AI. And I see it more like an aesthetics of the sampling. So in my work, I mostly been experimenting with two main forms of sampling. So on the left is sampling in continuous space. For instance, a typical model would be generative adversarial networks, GANs, or variational autoencoders, VAEs. And this is just a kind of a simplified illustration. On the right is the sampling in discrete sequence, which actually link to the discourse in the discrete. So examples would be pixels RNN, pixel CNN, or WaveNet, or self-attention models, or even transformers. Transformer architecture, like GPT-3, things like that. So here, in this case, just an illustration of the pixel CNN architecture. Yeah, very, very simplified. In fact, I've done a more useful ones for more recent publication for SUTD. This is the one for StyleGAN, which later on you will see some of the projects implements StyleGAN for the generation of architectural forms. So let's get back to the theory of architecture sampling. Three key hypothetical claims that I would like to share. First is the semantics, and then the structures and the perception of architecture sampling. So essentially the first one, the semantics of sampling, what on earth is sampling, right? What does it mean? Is there some kind of historical references? So if we think about it, sampling can be, in the early days, it's understood as more from a pedagogical way of thinking. is essentially what the Victorians would do to teach young ladies, to do cross teaching. So it has that idea of teaching, learning, right? And the middle column, which is probably the more important one, is the image in the middle. Is the idea what is actually showing these analog to digital converters. And by default, to do that, one has to sample, meaning discretizing and then quantizing, which means binning them into specific values of discrete values, in order to then use it for digital purposes. So there are some underlying technological and pedagogical references. And of course, the aesthetical, which is closer to what we're doing these days, will be the non-parametric and parametric way of learning. Like here in the first example, for instance, back in the late 90s, this texture synthesis algorithm, which is kind of doing the same thing as what we're trying to do by synthesizing different images with GAN, but in this case, it's non-parametric. Unlike the deep learning models, which are parametric, meaning it is based on the parameters of the different neurons within the deep model. Of course, actually, back in 2014 was the Ian Goodfellow GAN. And the structure of sampling, this is interesting because it questions how, just like in natural language processing, you sample as a sequence. Just like texture synthesis, you sample as a grid of pixels. But the question for architecture is, how do we sample? With what structure? And there may be many structures, but what are these? How are these ones supposed to be encoded? So earlier on, if you even look back at some artwork from Gordon Martha Clark in his Project Bingo, he literally sampled the whole facade, right? Cut it into 9 parts and then take one part of it and put it in a museum. Or even Rachel White-Reed in her Ghost project, basically using a grid to cast the interior of the entire Victorian house. Or even to the most extreme, the Japanese version of Peter Eisenman, Hiromi Fuji. He literally overlaid a grid on every single surface of his building. I mean, real buildings. Yeah. On the computational side, Lionel March, for instance, he was already talking about encoding and decoding of floor plans as Boolean matrices. So the sequence, in this case, we've seen a bit, is related to language modeling. We see form as a sequence of tokens, meaning say a sequence of characters, sequence of words. And these idea of a sequential understanding of architecture was already kind of previously explored by many people, right? For instance, Bernard Schumi in his sequential house, or the Ashizum, the no-stop city, which is basically typing, right? The typewriter to create these symbols. And of course, more from a hierarchical understanding of structure would be these graph-based or directed graph, directed acyclic graphs, for instance, of grasshopper even. Of course, it's different, but this idea of a graph is is pretty crucial, and even the Markov transition metrics between nodes, but these are not that important at this point in time. The third one, which is maybe more easy to understand, would be the perception of through sampling. So what do we perceive? Is it the idea is that it is actually necessary to debunk 3 formal bases of our architectural training thinking, which is essentially the idea of figure ground, the idea of parts and whole, the idea of shape and grammars. So if there's no figure and no ground, what do we do? Well, we treat every single piece as the same thing, right? Just sample them. If no parts, no whole, so we don't even think about even what William Mitchell first talked. He talked about the semantic lattice, the whole to parts relation of the temple, or the classical chair, where every part serves a specific needs, specific role, or shape grammars. there's no rules anymore, no shape rules, for no grammars. We just do the statistical understanding and then generate the form probabilistically. So if there's no figure, no ground, then what's left? Well, it's a flattened world then. If there are no parts, no whole, then maybe it's just about the resolution. And no shapes, no grammar, well, no rules. We just do statistical understanding and generate probabilistically. So to illustrate that three privileged modes of architectural representation and perception, I will just show three examples. In this case, for instance, on the left is, well, I kind of redrew this Stan Allen field condition from 1997. Typically, we are trained to see this way. It's sketched out, essentially. We perceive these as single black rectangles. But actually, if you think about it from a convolutional neural network architecture way of seeing things, then we are actually convolving across and just grabbing the patterns. We don't care whether it's black or white, we just grab the patterns. So it's essentially kind of a machinic vision, or no parts, no whole. For instance, in this case, the Berlin chair by Redfeld from 1923, the distilled period. A machinic way of seeing then would be likewise looking at the different resolution, right? So in this case, for instance, it's showing different semantics, different patterns based on different resolution. They are very different. Just because they are taking on a very different granularity. And lastly, the revisiting of the histogram architecture, which, well, if you actually encode all the examples from the histogram architecture of the 1969 by Super Studio, they're basically numbers, right? Just a metric. So we don't need grammars. We don't need, my earlier on in 2019, I wrote a chapter for this the discrete edited by Jules Redzin, and that was one of the earlier paper that tried to articulate the idea of sampling. So here are a few quotes from the Super Studio. So for them, the idea is to arrive at a generalized reductive process. Fine, they have a different cultural context back then in Italy, in Florence, but the idea is that the histogram architecture by the Super Studio already suggested this learning from a catalog of forms without rules. And they try to generalize it, not just for architecture, but for everything, meaning furniture, environments, cities, anything, effortlessly. And of course, they also predicted the death of the architect, meaning you have this generative system that could generate anything and therefore dispose architects completely. So this is a follow-up, or this is actually part of the exhibition for the Venice Biennale. Essentially 3D printed of the transformation between a chair and a building. In 3D printed in that 3D latent space. So it is at this juncture that it is necessary to differentiate the notion of form finding between that of form optimization and that of form hallucination. So I'm not talking about these other other generative form finding processes, though themselves are very useful and interesting and rigorous as constraint-based optimization of structure and material. But what I'm trying to talk about is the GIF you saw earlier on, this reconceptualization, this possibility to reconceptualize form regardless of its meaning, of its ontology, meaning a building and a chair is, if you want to explore in 3D, it doesn't truly matter, or at least in the conceptualization stage. So, one of the project, the chair to building or chair to anything, in fact, project was actually featured in the 2020 NeurIPS. NeurIPS is actually quite a well-known conference for AI, and they have this annual AI art exhibition. So I thought this example, a close-up would be useful. So we see that this is not the most structurally sound chair, with strangely incomplete backrest, leg support, even seat itself, right, is kind of, perforated or missing. Yet there is this property out to it, this uncanny familiarity, like a chair, yet like many chair, but yet not quite. In a sense, it's not about optimization, structural optimization. It's about the computational subversion of existing form finding paradigm. In this case, the structural optimization. So let's go into the continuous space example. I'll just skip these, but essentially the project looks at the 3D, basically having 3D buildings, public housing in Singapore, and learn their geometries. And the idea is that whether we could create a new architecture that is simultaneously in every architecture. So this is Singapore for those who are not familiar. Should keep track of my time. This I'll skip. So these are the data points, right? All the public buildings, housing in Singapore. A quick, Singapore is tiny, just an island. So that outline is actually Singapore. So the idea is that we learn from these housing, high rise mainly, both in massing and in texture, and in semantics, meaning the circulation and all that stuff. But first cut would be understanding the shape similarity and dissimilarity. So in this case, a T-SNE or UMAP way of looking at high dimension to understand our data set first. Of course, then we look into the voxel representation in this case. And here what we see is that these are not just white voxels. These are not innocent voxels with no probabilities. Everyone has a probability that suggests whether it should exist or not in space. So what we see on the right is the probability distribution of every single massing. In this case, every voxel approximate to about 3 by 3 by 3 meters. So we see that it's working the latent space. I'll show you other ones, but this is also the point to talk about the plasticity, constructive and the destructive version. We could actually frame this, those who are familiar with GAN training, there's this problem of the mode collapse, which means the model refuses to diversify. And in that sense, is converging into the sameness of form, or you can call it a type. But it's actually destructive. We actually see the building, but missing a lot of the plausible kind of logic to what a building should be. So we also, here we see much clearer. We are looking at the probability. Therefore, the one on the right is actually a very, not very confident kind of form, because it's not sure if it should be black or it should just disappear. And in this case, this is just a glimpse of the data set. Maybe just skip a bit. So this is a data set that we have, not the most interesting buildings, but public housing, so you can't expect too much. And then the forms, but the key thing is the semantics. The semantic meaning, where are the lifts? Where are the terraces? Where are the roof? And all those very important stuff, because we're talking about not just the exterior, we're talking about the interiority of form. So the first cut would be, so changing these into the semantic. So in this case, the red color represents the public spaces, the green, the apartments, the blue will be the vertical circulation. So we've got this. And now we want not only to learn binary representation of voxels, but the semantics. So we are now walking in that latent space embedded with semantics, these architectural semantics. A glimpse of the semantic latent walk. So in the beginning, the GIF that you saw just now, I'm just kind of having a still frame for you to just kind of see the difference as it transforms itself. And here's a training. I show a few snapshots of the training. So in the beginning, it's just kind of figuring out what to do. At some point, it looks like a broccoli or something. And eventually, it seems to generate something reasonably like a building. And at times, it looked like a teapot or something else, or a building that kind of floats around with certain parts missing. And also these other ones. But sometimes the not fully perfectly trained ones are actually very interesting. So let's visit the same thing. So we've got that latent work that I showed you just now. How to then architecturalize it, right? So in this case, this is also, this model took much longer, took about 2 weeks or so to just train it on the cloud. You can't actually do it on Google Colab. Well, especially if you don't have the Pro, but even if you have the Pro, you have difficulties. So in this case, another kind of slow down for you all to see is that it's transforming and it's doing latent work. But these, if you look closely, we could see the staircases. We could see the apartment units, the kind of communal spaces, the water tanks. Well, this is not an animation. Yeah, so the same thing I saw in the beginning of the lecture, but a closer look. So we see staircases, walls and floors, morphing based on the through that latent space using that learned embeddings. So the discrete sequence, which is something that is also I'm very interested in, which I tested it out also with some students using more toy examples. So I thought I could also show that. So in this particular case, although I was using the continuous sampling as the promo, it is about is using a transformer-based deep learning model, which is a combination of self-attention, encoder, decoder, and also autoregressive, meaning autoregressive in the sense that is doing ancestral sampling, meaning learning from previous, like a sequence, essentially. So it sequentially learns with some pre-decided discrete embeddings, and then sequentially generates with discrete sampling. So here, for instance, is an example of the output in the workshop, is that, or there is a toy example, right? So on the right, we see that it's sequencing, is generating one edge at a time. Well, actually, the points and then the faces. You'll see in a bit some examples of the training process. So quite different from the voxelized thing that I showed just now. This, we're dealing with literally just vertices and faces. Is the most elemental representation in. I think Theo Van Dalsman might be happy with this. So in this project, it's basically combining different forms, the tree structure type of form with some equilibrium loading done, and more volumetric furniture. So the training might, well, actually, sorry, there should be a video maybe of that. Oh, okay, it's later on. Sorry, give me a second. So it's in progress for in the lab. I'm currently working on the textures as well. But I'll show the one from the digital future, the examples. So here again, that thing. So the idea is we sample not voxel, we sample vertices, and vertices gives the basis for the faces and the edges, and therefore you see that it's sequentially generating the connectivity. So the data set. You see that during the training, we see some glimpses of distorted furnitures, right? Struggling to become a chair or in between. And you have other, oh, this is not the case. Okay, this one you saw. But it's the same thing you see in the video. So we sample at one point at a time, just like speaking, right? Speaking one word at a time. And then we kind of figure out which are the points that we should sample to make a face. So you see that the line that's connecting that's the actual sequence of the sampling process. Sampling in this case, I'm talking about inference. not in the terms of getting a sample of inputs. Yeah, the training of other stuff. I think, Paul, I have to end in 8 minutes, is it? Or do I have a bit more time?
You can go. Yeah.
Oh, okay. Right. Thanks. So some student looked at courtyards, how to combine topography and courtyard design, or even particular buildings. The reason why the results are not that amazing is also because of the computational hardware problem. We're just doing on Colab for these new students that are not familiar. It's just easier, but actually we should train more than the time that we have at a workshop. But anyway, so some earlier experiment that I was doing way before 2018, I think, I was looking at the Bauhaus. I was interested in this elementarism of surfaces and with very in a distinct sense, right? And so in this case, you see times of overfitting, meaning is the machine learning model is memorizing, therefore it's overfitting. It's doing the exact thing. At times it's underfitting, so it looks like it has no capacity to learn enough, therefore it's just throwing rubbish out of the generator. So sometimes we see the this kind of recursive copying. That is a sign of overfitting. I thought I'd show this fun project, which is a paper published some time ago. This is game design, but the idea is the no-stop city Pokemon, right? So if we understand, if we interpret the ArchiZoom as this sequence of generating, of course he wasn't using machine learning, but the idea is the same sequence. So could we actually generate different Pokemon game levels that are playable? So here is a no-stop city Pokemon. And if we go a bit deeper into what on earth is going on, we can actually see the semantics a bit like, so here we're doing the decoding, right? So those who are familiar with machine learning, we have this encoding process. So in this case, just kind of encoding them based on different characters in Chinese. So we could see that just figure ground. If this is just figure ground, and then this is the semantics, which is kind of close to what I was showing previously for the public housing. But in this case, this is a very simple version of just 2D, right? Figuring out if the space actually worked. So sometimes the orange one will be the buildings, and the blue ones are just the water bodies. This example, which is probably more understandable because most people are familiar with the Barcelona Pavilion, is to also sample it, right? But now we're talking about not in the large data set way of thinking. It's a small data set, which sometimes is good enough. So in this case, what we're seeing here is a no-stop city Barcelona Pavilion variance. We see certain characteristics. So the idea is, here we have the floor plan, right? In a neuroplastic way of thinking, typically, is to just, the elements would be the walls, the glass, the floor, the planes, essentially, the planes. But from a machinic point of view, if we just do a 2x2 sampling, we get this. And of course, if we do a half meter and half meter, we'll get this. If you remember from the previous example I showed you, the Berlin chair, they would actually create quite different semantics just based on resolution. So if we compare 4 different resolutions of the Barcelona Pavilion, what we get without a full convolution process, we get about the same number of states, but they are different, right? This is just to show the scale of the tile. So here, normally, if we just learn something, a form with uniform probability distribution, we generate rubbish, right? Like here, no learning, all nonsense. But even if we learn the frequency count of each piece in the training set, is also not very useful because it's not sampling the spatial relation, which is critical for architecture. So we also get nonsense. And in this case, this is when we could bias the generative process by biasing this artificially biasing the learning, right? We're saying, bias towards the horizontality, the horizontal direction, or the vertical direction, which means that the same model, given different configuration, not in the sense of a rule, but in terms of the probability distribution, we could actually create quite different stuff out of the same input training. So in this case, we essentially is changing the receptive field of being more inclusive of the horizontal and vertical. We get something closer to Barcelona Pavilion. And essentially, in the end, we could generate, again, just like the other examples, we could generate different ones with different similarities. This one I won't go too into it, but this kind of combining the static cores with different receptive fields. So like a different kernel in the way we speak about convolutional neural networks, it will be the different size of the convolving lens receptive field. Barcelona Pavilion, for instance, we could break it likewise. So here, if it's just 3 by 3 by 3, we get about 447 unique patterns. But actually, we're not just splitting them, we're learning the relationship and the probability of neighbors, right? In this case, for instance, we're learning what's going on. So given a much bigger receptive field, we get 10 times more patterns. And again, we can do the same thing, right? To learn the relationship in 3 dimensions. So here are examples of doing arithmetic of, say, minusing, like the bottom row, minusing the staircases. Do we still get mesodomino A or mesodomino B? B meaning the NT 5 points of architecture mesodomino version, shear walls and all that. And we do see the generated output having those desired characteristics. Other AI stuff from the AA, this I just skip quite quickly. So I was playing with neural style transfer back in 2016. My students were using Tiano. It was very tough because just doing the dependency would just kill us off on the system. But anyway, so here are some examples. Even doing the semantic, now they call it pix to pix, right? In 2017 is a different model. Both 2016 and 17, we're looking at the optimization, meaning kind of playing with the layers of pre-trained networks, not training again from scratch, which is the case for, say, pix to pix or CycleGAN. Some 2000s, this is really old. Back then, got pretty much nonsense, but it was fun. And then that's 2017. This I'll skip. But this is only to show that we don't always have to choose deep learning in a sense to do learning, because even doing eigen decomposition, we could learn the principal component of a form and then generate them, and then do kind of a latent one, because it has these vector representation, like here on the left, you see all this stuff going on. But anyway, this is a 3D version of the eigen decomposition. Meaning looking for the most important, assumingly they are linearly separable. Stuff. These are some things I was playing with my students in SUTD. So AI facade, the idea of making a facade age or look younger, I find quite funny. So this is one clip, how to audify a building. So it's easy, right? It's just train a model that has, based on the training set of older and younger building. But of course, older and younger is very debatable, right? Modern buildings tend to look younger because they are textureless. But the idea is that we can actually use it for more practical purposes, building maintenance, for instance. Youngify, essentially, they just make any building that the model sees any building and just make it modern, meaning just flush and clean walls. Some examples of the generated outputs, input and output, they age pretty tremendously. The other one is the alteration, whether one could learn in parallel, right? The before and after. So this is doing the latent work in parallel, where we could see that the before alteration, after alteration. Of course, there aren't that many data sets with such type of these are image based, which is fun for my student, I think, to play as a start when the 3D part is a bit tricky. So this is quite fun. So then to analyze the before and after, even to kind of draw, to somehow understand the compositional transformation, right? Sometimes we see scaling, sometimes we see dividing or adding of parts. Also then inferring the interior. This is also for fun. For those who are Japanese fan of anime, for instance, it's just a hallucination of the Studio Ghibli's movies, right? There's lots of architecture stuff in there, and it's fun to do this. But the other part about this is to then not just generate new anime, but also to figure out how the machine and the human sees it. So the subsequent test was to actually ask a human to describe the image, and then ask the machine to say something. And turns out that, of course, the human is a bit more poetic in well, it depends on who, right? More poetic in captioning, whereas you get quite boring stuff. But you can see that there's some spatial understanding of the human compared to the machine, right? So for instance, it sees a house with a wooden bench in front, but actually clearly it's not a wooden bench because it's perspectively wrong. Other project like the pavilion. So if we can't build because of COVID 2020, so what do we do? Well, just learn and just generate a new pavilion, right? Don't have to pay anyone, don't have to install anything, just generate, and then we can have many versions of it. But the idea is to also learn certain features. We see John Lavelle kind of stuff, and Peter Zumthor, and instances of the OMA project also, I think. So we've got lots of stuff, right? So here we even get the more recent pavilions. And then train a model to figure out which pavilion ought to belong to which architect, right? So again, looking at the probability distribution of this categorical distribution, right? So this also, so for instance, here we say, okay, fine, that is clearly more Frank Gehry than Zaha or something else. We could look at these, because the end layer of the neural network for prediction is the softmax, right? Which basically gives you this distribution of probabilities, and you just see whichever is the highest or second highest. We could then have a different understanding. I'm almost done. So if you're interested, there's this other website, artificialarchitecture.ai is not the one for more serious research at the CTD. Is a more kind of a sandbox thing for me. So you can have a look. And also the AI architects with Daniel Bulajan, Matthias Del Campo, and Sandra Menninger. So our styles, whole things are there. I mean, representative stuff, yeah, there. You could find out more also. And then the forthcoming book chapters, if you're interested, I'm publishing 3 books, 3 chapters in spring, one for Stanislaw Shiloh in spring 2020, and then Newlich, the AD, Matthias Del Campo as well. I think should be spring as well. And Philip Yuan, the draft has been kind of, I think they are kind of just preparing, so it should be out sooner, I think, called Machine Intelligence. And lastly, this is the last slide, is my own book, which I published like late 2020. You could, if you're interested, you can get it. You can scan the QR code. According to Newlich, it's supposed to be the first book published on the subject of AI and architecture. Well, I suppose AI in this case, we're not talking about straight grammar, so we're talking about deep learning. Yep. So this is all I have.
Thank you, Emmanuel. It's a fascinating lecture.
Thanks.
Thank you.
Thanks.
Mon, can I maybe ask you to start off the conversation like I usually do?
Absolutely. Thank you so much, Immanuel, for that dense yet clear presentation. You stepped from form follows growth to neoplasticity to GANs to sampling and reimagining pop culture, but the sort of AI sort of implications of that. I think one of the questions that always pop into my head as you start exporting, let's say, your creativeness to the machine, how do you have that dialogue of maybe what failure and success is? Like how do you judge what is good or what is bad? Like you talk about like, oh, this wasn't good or that was good. Like you have these sort of interesting relationships with the sampling, as you call it.
Mm-hmm.
Could you step us through that a little bit?
Right.
And what's your thought process as well in that?
It also depends on the task at hand. So if one is exploring the capacity or the capability of that particular model, then we'll be looking at something quite different, right? We may sometimes deliberately train it till it overfit, so it just copy, right? So that we can figure out its performance. So that is when we are kind of adjusting the hyperparameters or changing the details of the structure of the neural network architecture. But more from if we're exploring ideas like what my student was doing, we often have this problem, right? You generate lots of stuff and then now what? What do we do with it? Right? Like the kind of style GAN thing. And is to figure out which one makes sense. I mean, humanly speaking, right? So if we can translate some of the 7.5 million to real stuff, on the one hand, we want to look for something that is familiar enough, but not too familiar, so that it's interesting and seemingly plausible to construct, right? So that may be the criteria. But for me, it's always looking back at the training set. Like, is it really doing something intelligent, like cool, right? Or is just, if like some people in the past were saying like GPT-3, the language model, it learns a lot because it really learns a lot. Therefore, it may be just like reproducing the same stuff nobody knows. So for me, often these are some of the factors that I'll look at. Yeah.
And
also
almost feels
post-processing,
like
right?
I feel like it's almost like it's adding more than what we can imagine. It's almost like sometimes we're like just showing us that chair or showing different ways of me's. Like it was funny because I almost think that you're trying to recreate architects in the day of today. So for example, have you seen the next Rembrandt, that project that was done, that they sampled a lot of Rembrandt paintings, and then they imagined if Rembrandt had to paint another painting, what it would be. I can almost imagine you recreating what art, like architecture that Le Corbusier does. You create an AI of Le Corbusier, and then he does a building of modern day, and something that happens in that. And it's quite funny that you sort of do that through Mies, you do that with the domino, and you even do it with like Pokemon, right? And my question would ask, like, have you considered this for Minecraft? Because it seems perfect.
Actually, my student did some with Minecraft. We did it Minecraft with the variational autoencoders. So yeah, it's
just because it's in this digital world. It doesn't have to be, like physically built. You can imagine it. You can experience them. There's just so many layers within that I feel could be a nice project, I guess, from the readings that I saw.
Yeah, there are many ways to go about it. And talking about the idea of seemingly trying to reproduce the dead architects, right? So for the AD publication, for instance, the Miss Van der Rohe, previously I submitted a few stuff and they have something, they were saying that there may be a copyright problem. And then we're saying that actually it's not the same, but it looks similar. So is it? So it's quite funny. Which is a success, I suppose, meaning sorry?
No, can I pick up on that point? Because I think, Mon kind of insinuate that the work is trying to, with the Rembrandt project, that is about, to me, is about mimicking Rembrandt. And I think my reading of your work is not necessarily about mimicking, but in fact, a kind of a deeper, if you like, kind of a further deconstructions of language. And it's quite interesting that you were referencing Melbourne's earlier students of Derrida, and in a sense, it's kind of going beyond that deconstructivism of syntax. I mean, on the kind of questions around kind of very similar to what Mon is kind of asking earlier, but perhaps you may maybe expand a little bit more on this notion of, you know, you apply this semantic over kind of formal forms in some of your earlier work that you were talking about with the kind of this in the Singapore project, for example, the housing project. I think to me, what is interesting and what is slightly different from what genetic algorithms tend to produce, which also produce nonsense most of the time, is that I think there is a certain degree of familiarities, and I think the syntax is almost starting to take over. So I'm wondering, would you be able to maybe expand a little bit how the syntax is actually perhaps different from, let's say, a GA method of generating form, because that has also a relational kind of parts to it, if you like. But with those forms that you generated, it seems to almost have an architectural, a spatial kind of language which is ingrained into it, which generative algorithms almost kind of ignore, right? Because it's almost so fundamental that everything, as long as there's a face, it can be edged together. So it's purely geometric in that sense. And I think in a lot of your work, I found that there's actually partly also a spatial relationships inscribed into it. And I'm wondering if you can talk a little bit more about that.
Right. Thanks. I'm not an expert in GA, but from my understanding, is this idea of the chromosome, right? Just kind of looking for the fittest. So there are already very clear so-called constraint. If I'm not wrong, please correct me. Constraint that they should optimize. But if you talk about like the GANs, for instance, I mean, the optimizer and the loss error, that sort of function is actually not directly related to the task at hand, right? We're not talking about this, the optimal height and whatever, or I don't know, solar radiation. It's a different thing altogether. It's so generic that after that, it can be like this. So there is a major difference. And of course, GA has been considered one of the most powerful algorithms that, for instance, Margaret Bolton, the famous author, professor who wrote about creativity, computational creativity, GA is actually considered the third class of creativity, transformational creativity. So it has the ability to transform its search space. But if you compare to generative adversarial network, this is even more crazy, right? I mean, it's changing its design space every time because it's trying to figure out, right? So, and at the same time, the beauty of this deep learning model is that, like GAN, it never quite seen in fact, never seen the real data, right? The generator is just keep on generating. It had no idea how the real thing looks like. It's like trying to guess, right? With your eyes closed. So it's, from a kind of intellectual perspective, it's very interesting. So, but in terms of the generative power of, I don't know, GA has this need for explicit parameters to optimize. That's the slight problem. And also maybe that's why it's also more immediately useful for architects who could immediately identify the parameters. But for, say, exploring or ideating is less effective, I think.
Yeah. I think
what interesting to me, at least.
Yeah, I think in a sense, it also, in many ways, the GA models almost ignore the, I mean, it very much kind of ignore the kind of the spatial aspects of it. I think to me, there is something quite spatial about your work. Even in the MES project, there is really a kind of, you're talking about this notion of a bias, right? The bias are spatial, and I think
actually it's true. I forgot to respond to that. That has to do with the structure or something, right? So my investigation back then in EPFL was to find out, is there even such a thing as a sampling unit, right? So natural language processing just tokenize every single word. And for signal, this audio signal, just grab the signal, done. But what's architecture? And my conclusion is that actually there isn't such a thing. it's up to the designer to figure out what's the sampling unit of architecture. Some may choose to do it as a vertex or face. Some may choose to do voxel. Doesn't matter. As long as you have a way to kind of, in a structural way, to learn these, say, tokens, these samples, then fine. And they, of course, would perform very differently. Therefore, I kind of mention convolutional neural networks quite often because it is inherently a very spatial thing, right? It knows its local neighborhoods, right? It's just kind of scanning around. But the problem is the invariance to other stuff, right? So the eye of a person's face, I mean, may appear somewhere else because it has no global structure. That's the problem. And that's where the transformer comes in quite interestingly, because it's able to learn all the way back. Meaning, I mean, if you have a kind of a string of words, you kind of turn it into an image. It's just, just go like this, right? So it can actually learn its past history quite well. So it has a global picture better. And then if you add in the attention model, it's attending to important parts of the, say, tokens of pixels, and then you can figure out. So yeah, am I going off track? Yeah, so
no, you're not going off track. I think that's what you say is super interesting. I mean, I guess the reason why I'm also partly interested is in maybe leading on to the next part of you're talking about machining viewpoint. So the unit in this current visiting school, myself, David Leggett, and Stella, it's running the unit, and we were only 2 days ago with Stella's lecture talking about body without organs or organs without body. What there's sort of explosions of neural network, the kind of flattening of non-hierarchical kind of structures. And we were being very much talking within the unit about how we can start to re-look at the world behaviors around us through machines, languages, right? And I guess to me, a lot of your work, almost all your work have this kind of particularity through kind of machine learning, but also to dissect the way that we view and look at spaces in, as you call it, kind of the degree of resolutions, whether it's this much or that much. And I think to me, those are super interesting because it sort of suggests a different way of reading architectural spaces and also elements. And I thought there was a really nice twist on how we can start to reuse machines, not just as kind of a passive fabrication tools or as a kind of as you kind of said, this Ivan Sullivan's model of drawing input output, but actually as a kind of a feedback system. In many ways, your work almost rely on that feedback, but that feedback almost go like what one would consider a single feedback. You are multiple in a sense. I mean, I guess the question
is actually slightly different from the cybernetic way of thinking.
Right.
Because
would you differentiate that for us? Yeah.
Yeah. Because I mean, unless you talk about second order or whatever, but anyway, just do first order cybernetics, right? It's feedback, and regulating, right? It's adaptation. So that's why I thought the growth Darcy Thompson stuff is pretty interesting, right? We're not trying to hit some kind of equilibrium, some kind of optimal equilibrium in that sense. Where and so kind of removing the function from the form, right? Or fine, some may say this is just irresponsible discourse about form finding. Fine, but in any case, it's interesting because some use the hallucination idea that it can find form and all that. So there is a key difference. The other thing actually I want to mention is, the GA thing actually, because Malibu also said things like, there's a shift, right, from genetic to epigenetic. Genetic is this combination of the DNA sequence, right, the genes, right, just basically recompose them, right? But epigenetic is this secondary layer that has the ability to change the given gene, which basically the things that you got after you are 2 years old or so. It has the ability to change it. So in that sense, it is what if we use the theoretical framework of Malibu, then this plastic deep neural model because it's always changing the weights, right? It's actually essentially plastic, but we're not at the point of even changing the connection. That is a different thing. This is like the edgy research now, right? How to have a deep learning model that could just reconnect, remove layer, add layer when necessary. This will be awesome, but we're not there yet.
The ultimate neural network, eh?
Yeah, just add 5 layers if you want. If it's good, 2-3 more layers.
Mon?
Yeah, I think on my end, it's quite interesting how you show these different formulations or mutations of objects of things that we can relate to, right? Like buildings or chairs. But inherently at the end of it, this object that you're, I guess, sampling or designing resides in the digital world, right? Like it resides in, because you're not supposed to fabricate it, I presume.
I'm fabricating the one for this AI sampling Singapore. So the building that you saw on the first page is morphing with the semantics. That one I'm currently fabricating. Yeah. And so of course then you have the post-processing of structure.
Yeah, so then I think that relationship with this digital world that you're playing around with, and how you're saying that you're not interested in structure or form where there is no gravity, to the translation of the physical world where there is this confinement of nature. What is that relationship, right? Like when you think about it, like we design and then we start simulating reality inside the digital world because we want to understand reality more. But you have this sort of vacuum in a way that I'm not interested in, like structure, I'm not interested, but then inherently you sort of make it in the real world. And I'm curious on your position on that and why you're doing that.
Right. So actually, not that I'm not interested in the structural part, but I don't want it to be the so-called a priori, right, of the design generation. So that's why I was showing the Autodesk, is it the project Dreamcatcher or something, where it's about kind of it's pretty decided, right? The load's going to be there, and just minimize the amount of materials that you need, and done. Right, we're going linearly, right? I'm fine. Sometimes they do different connection, but essentially it's going to be a chair. Whereas what I was trying to show, this kind of morphing between even buildings of different things of different scale, in the way of speaking, like the super studio, right? Doesn't care if it's furniture or building. We are exploring 3-dimensional forms, regardless of their supposed function. Supposedly to be a chair or building, fine. We're still exploring. Just like when you look at GAN generate image, it's interesting because we can't figure out how to make sense of it, right? And if we could figure out something, understand something, then we are actually quite happy because it becomes useful. So that's why I'm not saying I'm not interested in the structure, but rather they ought to come in later. Of course, in the right political way of doing architecture is that it's all in parallel. So, however, at this point in time, I'm just not as interested in the optimization.
But that's a valid point. I think that's a valid point, though, because if you think about it, like to be creative, you have to think differently, right? Like you have to think about things in a different position or a different angle. And I feel like you're providing a lot more discourse into the subject that this isn't the only way to think about AI. Like people always think that it's the most optimal, it's the way, like we're going to recreate stuff. It's like so functionalistly driven, right? Not in a playful sort of what are the opportunities or what other things could emerge from AI that architects from a different sort of lens can look at. And I feel like you're providing us with that in a really rigorous way, and I really enjoyed that. And I feel as though that if you really focus on that obsession, like it's almost like things would come out of it in a different and unique way that you wouldn't have thought of if you put all these restraints on it in the beginning.
Yeah. And also it's timely because it's still quite young, right? This whole AI architecture thing with deep learning. So we should make use of that space for exploration.
And it's based on computing power, right? And how long you can actually do it. Like I see this as the beginning, is almost like when the internet was its infancy, when resolution of screens were really low. We're in the beginning of how AI can process this, and right now it's just a 56K sort of image. Like it's going to only get a higher resolution, and as it gets better, I question the role of the architect as well, like speculating about where it's going to these, like, because biological forms like us, we are going to pass away over, let's say, 100 years, but these GANs, these algorithms would outlast us if it keeps on going. So ultimately, these things would actually be able to recreate things with a lot more consideration and parameters than us. And where is the role of us in this machine? And I think that's, maybe a conversation for another time, but also births all this philosophical, ethical questions as well.
Actually, the resolution question is quite interesting. At what resolution do we need for that architecture task? But if it's extremely high resolution, in the end, like experience that I had with my student, they did some GAN stuff. And they said, well, actually, low res is quite cool also, because I can't figure out what on earth is that. Whereas high res, it has decided for me already. I have no other way to think otherwise. Yeah, anyway. Sorry, Paul.
It's like that Impressionists, right? Impressionist painting.
Yeah, it has that space of ambiguity.
Ambiguity, yeah.
I think we can sit here and talk about this all day. But I do have to stop this conversation, I'm afraid, because I think Immanuel needs to go on time. But thank you, Immanuel, for a really amazing lecture and such a kind of thought-provoking kind of topics. And I think you and I will need to have a conversation another time.
Yeah, sure. Thanks.
And I really appreciate you bringing the conversations of a different viewpoints, using kind of machine vision learning and from the machine kind of viewpoints to the visiting school. And thank you very much. Mont, do you want to say the last word? Now I need to share the slide to close.
Yeah, absolutely. Well, that concludes our lecture series for the AA Visiting School. And in our second week, we sort of looked at Stellark as a sort of site or body to operate in, with the vast scales from Oscar and Adolfo yesterday on a planetarily to a continental level, to now in the digital realm of looking at resolution through different lenses of sampling from Immanuel. I feel as though that being an architect of today is so exciting. There's so many different sites and parameters that we can play with, explore, and even give back. So on that level, I would encourage the students to really focus maybe from that word of obsession and play with that and see what we can do in the next few days and see where this visiting school can take us.
Thank you,
I'll
Mont.
hand the rest to you, Paul.
Thank you, Mont. And thank you, Immanuel, again for the lectures.
Thanks.
So this concludes our last of the AA Visiting School Melbourne's lecture series. Next week, the MSD at Home series continues with Luis Basabe's titled Multiplayer City, Flexible Urban Support for Complex Social Processes. Next Tuesdays, and following that, we have the Dean's Lecture series by Kochakrum Varunhum on landscape porosity, why we need water-based urbanism. Thank you very much for joining us. We'll see you at the next MSD at Home series. Good night.